Hello, chemists. This is Ms. Placino, and you're watching lesson 9.7 on Gibbs Free Energy. In today's lesson, we're going to talk about reaction spontaneity and how we're able to predict whether a reaction will occur spontaneously or not. We're going to be doing some calculations in today's lesson, so you probably want to have a calculator handy. Goals for today's lesson. You should be able to explain what spontaneity is in relation to a chemical reaction and physical change. We should be able to use the signs of delta H, change in enthalpy, and delta S, change in entropy, to predict delta G, which is the change in free energy. And we should perform calculations using the formula delta G equals delta H minus T delta S. These last two are the big ones for today. All right, let's dive in. Let's talk a little bit about spontaneity. So we've got these two ramps, and I'm going to put a ball at the top of this ramp. If my goal is to get the ball down here at the bottom of the ramp, what do I have to do? Hopefully you're thinking you just need to tap it. If it's just kind of balanced there perfectly at the top of the ramp, it's not going to move. It needs a little push to get this reaction, if you will, started. So if I do that, if I just give it a little nudge, there we go, it takes off down the ramp. What do you think that little nudge, a little push is supposed to represent? That's activation energy. Yeah, I put a little activation energy in, the rest of the reaction takes off. Let's look at the opposite situation. Let's put the ball at the bottom of the ramp now. Ooh, there we go. If I want to get it up to the top of the ramp, back up here, is that possible? Yeah, sure, that's possible. What do I have to do? I've got to keep pushing that ball. So if I do that, if I push the ball, I can get it to move. I have to stay here to hold the ball. What's going to happen if I stop pushing and stop putting energy into moving the ball? Take it away. Ooh, it falls. Gravity's really, really strong in that section of the screen. If I want it at the top of the ramp, I'm going to have to provide the energy and push it all the way up there. I'm trying to draw a connection between spontaneous and non-spontaneous reactions using these ramp and ball analogies. When we talk about a spontaneous reaction in chemistry, we just mean a reaction that occurs under conditions that result in an overall release of energy. You might be thinking, well, wait a second, isn't that just exothermic? We talked about that a couple of lessons ago. That's part of it, but that's not all of it. Spontaneity takes into consideration both enthalpy and entropy. So the example with the ball at the top of the ramp is a spontaneous reaction. We put in activation energy. The rest of the reaction proceeds without any additional energy. And I guess now technically kind of their pictures are reversed, but when the ball is at the bottom of the ramp, that represents our non-spontaneous reaction. It can still occur. It just requires energy to get the reaction to happen. All right, so when we're talking about spontaneity in chemistry, try to keep these two pictures in the back of your mind, and maybe that will help kind of iron things out for you. When it comes to reaction spontaneity, we are going to be calculating what's called free energy. And free energy is a combined enthalpy-entropy function. All that really means is that it needs both enthalpy, delta H, and entropy, delta S, to perform this calculation. We know that nature tends to favor low energy systems. So we tend to see reactions that are going to have products with less energy than our reactants. When we go to calculate the free energy change, this is just kind of a word description of what the formula is going to look like. The difference between the change in enthalpy and the product of the temperature and entropy change. Don't get hung up on the wording. Seen the formula already. Delta G is equal to delta H, so the difference between the change in enthalpy and the product of temperature and entropy change. We know product means multiply, so we've got T delta S. That's really all that means. Delta G is Gibbs free energy, and just like with enthalpy and entropy, the sign of delta G is exceptionally important. So we'll be using this formula. And the sign of delta G is going to tell us whether this reaction proceeds spontaneously or non-spontaneously, regardless of whether it's exothermic or endothermic in nature, or increasing or decreasing in entropy. It kind of has the final say as to if energy will be released as we move from reactants to products, or absorbed as we move from reactants to products. If delta G is less than 0, delta G is negative, the reaction occurs spontaneously and energy is released. If delta G is greater than 0, the reaction does not occur spontaneously. That does not mean the reaction cannot occur. It just means that energy is absorbed. You might be thinking, well, wait a second, what if delta G is equal to 0? Well, then the system has established equilibrium, and you are a couple of units ahead of me. So hold on to that thought for a few weeks. Before we start putting numbers to the concept of Gibbs free energy, I want to think about this very qualitatively. So we've got this formula. Delta G is equal to delta H minus T delta S. And we've got 4 different possible combinations. We can have delta H as exothermic or endothermic. And we can see our delta S, our change in entropy, as either being increasing, so positive delta S, or decreasing, negative delta S. What I would like you to do is to try to kind of just plug those signs into our Gibbs free energy equation and predict what the sign of delta G will be and what that might mean. So pause the video, take a minute or two to think that over, predict the sign of delta G and the results. All right, so reaction A. If delta H is negative and delta S is positive, it'll always be a negative minus a positive number. Delta G will always be negative. Doesn't matter what the temperature is. This reaction is going to be spontaneous at all temperatures. So for T, it doesn't matter how big or small you make the temperature, that will always be a positive number. And delta G, when I take negative minus positive, will of course always be a negative number. What if we look at reaction B, where we have exothermic decreasing in entropy? Now I end up with like a negative minus a negative. So I can't say with 100% certainty what the sign will be. These types of reactions, exothermic decreasing in entropy, tend to be spontaneous only at low temperatures. I know the term low is very relative. Again, we'll start putting numbers into this in just a few minutes. Something like freezing, like water freezing and becoming ice, would be an example of change B. The process of freezing is exothermic. It releases heat. But going from a liquid to a solid is a decrease in entropy. You know from experience that you've got to get water down to its freezing point, about 0 degrees Celsius, to get it to freeze. So that would count as a low enough temperature in that example. Reaction C, we have endothermic increasing in entropy. Yeah, that's another one that I can't state that if it will be positive or negative in all cases. A positive minus a positive number can be a negative number if this T delta S term is big enough. What must be true about spontaneity in relation to temperature for reaction C? Good, this is only spontaneous at high temperatures, another relative term. Think about boiling. Going from liquid to gas requires energy. You have to put heat in to get water to boil. If the temperature is high enough, the entropy change going from liquid to gas is going to kind of be the driver of that reaction. And if I put water in an environment over 100 degrees Celsius, that change will occur spontaneously. All right, last but not least, reaction D. We have endothermic decreasing in entropy. From an energy perspective, this is the worst of all situations. That delta G will always be positive. Does that mean these types of reactions cannot occur? No, of course not. They can absolutely occur, and they do all the time. Positive delta G simply means that this reaction is never spontaneous. It will always occur and require energy to occur. A good example of that, photosynthesis. What do green plants have to have access to in order to make food? Yeah, they need the sun. That's its source of energy. So that's a good example of a non-spontaneous reaction that most definitely occurs. Let's practice a little bit with this concept. All right, so we're over here in your practice problems, and we've got chemical reactions, some balancing that you might have to do, good review of old stuff. You're asked to predict the sign of delta H, the sign of delta S, and then the temperature for a spontaneous reaction. Will it be spontaneous at high temperatures, low temperature, no temperature, or any temperature? Let's go ahead and walk through one together. Let's take a look at question 1. Take a moment, get it balanced. Give me a hint. Only one of those glucose molecules. Yeah. 6, 6, 1, 6. All right. If I want to figure out if the reaction is exothermic or endothermic, how can I do that looking at a thermochemical equation? Hopefully you're thinking look at where the heat is. In this reaction, heat is a reactant. When heat is a reactant, if we think back to lesson 9.3, we know that this is an endothermic reaction. Energy is required. All right. As far as delta S is concerned, how can I figure that out? All right, well, we can look at phases of matter. We've got phases here. So I've got 6 plus 6, 12 moles of gas on the reactant side. And only 6 moles of gas on the product side. This is a decrease in entropy. So if I have endothermic decreasing in entropy, what temperature conditions will lead to a spontaneous reaction? Good. No temperature conditions will cause this reaction to be spontaneous. This is actually the equation for photosynthesis, which we just discussed as a non-spontaneous process. Pause the video, try out question 2. I've gone ahead and balanced it already. Hopefully that's what you came up with. If we look at change in enthalpy, delta H, heat is a product. When heat is released, that is an endothermic reaction. Endothermic reactions have negative delta H's. If we look at the change in entropy, I've got 2 aqueous solutions as my reactants. I have a solid and a liquid as my product. So I went from mixtures to 2 pure substances. This is most likely a decrease in entropy. So if I'm exothermic and decreasing in entropy, what temperature or a spontaneous reaction occur? Yeah, negative, negative, low. It's actually how I remember it. Negative, negative, like subtract, subtract, I'd get a lower number. Add, add, that would be a higher number. That's endothermic increasing in entropy. I really like questions like this for your tests. You get to balance, you got to tell me about delta S, delta H, and tie it into Gibbs Free Energy. These are definitely worth practicing, chemists. Let's try to make this a little bit more quantitative. So question 11 is an example of a pretty involved quantitative Gibbs Free Energy problem. We are asked to determine whether this reaction is spontaneous at 100 degrees Celsius. Okay. We need to calculate delta G, but we only have delta S and delta H sub F information. In order to get to the point where I can apply Gibbs Free Energy equation, I have to find the change in enthalpy and the change in entropy for this equation. We know how to solve for delta H. Delta H is equal to, well, let's be a little bit more specific of the reaction, is equal to a summation of moles, the H of the products, minus the summation of moles, the H of the reactants. Okay, so we kind of plug and chug there. You might be thinking, well, wait a second, I don't know how to do that with entropy. Believe it or not, it's the same general calculation. The change in entropy for the reaction is equal to the summation of moles, the entropy of the products, minus the summation of moles, the entropy of the reactants. So what I'm going to do is walk through one of these. I'll go ahead and do the enthalpy. Why not? You can follow along. If you think you've got this, pause the video, figure it out on your own, and come back to check your work. All right, so I'm going to need Fe2O3. I'm going to need Fe3O4 And I'm going to need the information for oxygen. So make sure you're using the correct values. I'm going to work with delta H. So I want to make sure that I'm using these three particular numbers in order to solve for the change in enthalpy of the reaction. My products, I've got oxygen with 0, so I can just leave that out. Basically have 2 times Fe3O4, which is negative 118. I'm going to leave my units out for the sake of simplicity. 3 times for Fe2O3, negative 824. So I can plug that into my calculator and I can find the change in enthalpy for this reaction. I'm just going to round to the nearest whole number. I come up with 2236 kilojoules. This is an endothermic reaction. Pause the video, try out delta S. I'm not going to walk through this one. Once you unpause the video, just kind of the answer is going to be present. So just a heads up there. So when I calculate the change in entropy of the reaction, I calculate 133.5 joules per Kelvin. If you're wondering where the units came from, take a look at what we've got kind of in the header of the those columns. Delta H is in kilojoules per mole. I've taken mole times kilojoules per mole to end up with kilojoules. Delta S is joules per mole times Kelvin. I've taken that, I've multiplied by mole to end up in joules per Kelvin. So just be aware of where those units are coming from. Now I have the delta H of a reaction, I have the delta S of the reaction, and I have a temperature. So now I can use Gibbs free energy equation. Delta G is equal to delta H minus T delta S. Now, before we can just start plugging in the numbers and kind of grinding through the calculation, there's a couple of changes I have to make to my values. Can you find them? Let's start with maybe the easier of the two to find. I've got degrees Celsius. I have Kelvin. I need to convert my Celsius temperature into Kelvin. Hopefully remember how to do that. We just add 273. So 100 Kelvin is equal to 100 Celsius is equal to 373 Kelvin. So that's the first change. What's the second? It has to do with our energy units. We have kilojoules for the delta H. We have joules per Kelvin for delta S. I need to make sure my energy units agree. So I'm going to kind of tweak this a little bit. Joules per Kelvin. I want to try to turn that into kilojoules per Kelvin. I know that there are 1,000 joules in a kilojoule. So if I just divide by 1,000, I'd come up with 0.1335 kilojoules per Kelvin. And this is increasing in entropy. Once I've made those changes, now I can sub in. So I've got 2,236 kilojoules minus 373 Kelvin times 0.1335 kilojoules per Kelvin. My kelvins will cancel out, and I'll be left with an answer in kilojoules. Go ahead, grind through the calculation. What do you come up with? All right, so I'm coming up with delta G is equal to 2186 kilojoules, and this is a non-spontaneous reaction. I know that because delta G is a positive number, and anytime delta G is positive, we're going to see a non-spontaneous reaction. All right. If we kind of look back at the directions, it says if the reaction is not spontaneous, determine the temperature at which it becomes spontaneous. Oh geez. Well, let's take a look at what we know so far. we've got an endothermic reaction that is increasing in entropy. So if we have endothermic and increasing in entropy, what temperature conditions will lead to a spontaneous reaction? Yeah, we need high temperatures. We can actually apply delta G formula again. So delta G is equal to delta H minus T delta S. I'm going to set delta G equal to 0. I'm going to plug in my delta H again, 2236. In the interest of space, I'm leaving out some units. I apologize. And I've got temperature times entropy times delta S. Go ahead and figure out the temperature. Basically solve for T. So we should end up with a very high temperature. I'm getting 1.67 times 10 to the 4th Kelvin. The second the temperature is higher than that, this reaction should occur spontaneously. So the T delta S value becomes larger than the delta H. So we'll have a number minus a larger number, which will give us a negative delta G. So this reaction is going to be spontaneous above 1.67 times 10 to the 4th Kelvin. Wow, lots of work was done on this problem. So I've got my values that I've calculated. Delta G. I got you to apply, calculate change in enthalpy, change in entropy, use Gibbs Free Energy equation, and then use it again in a different context to figure out what temperature a reaction can become spontaneous. That is as hard as I can make these problems, and a lot of it is just pretty straightforward math. Easy to make small careless mistakes with punching things in and being careful with your conversions. But this is it. If you can handle questions like this, you are in really good shape with Gibbs Free Energy. Definitely take the extra practice problems and put them to work so that you can get better and just more confident with these concepts. All right, chemists, I know this lesson ran a little long. I apologize for that. Thank you for tuning in, and I hope you found this helpful.